The question that I have is, could you do an example on friction involving rods? We will keep things simple in this example. This is the problem that I have selected here, which involves just one rod. The rod here is this ladder AB. The wall here is vertical and smooth, but the floor is frictional with a coefficient of friction of 0.4. A man weighing 200 pounds is climbing on the ladder, and when he has climbed by a distance of 5 feet horizontally, he felt that the ladder is about to slide. We have two questions here. First, we want to find the angle at which the ladder is about to slide. We also want to determine the values of the support reactions at points A and B. Let's first go ahead and complete the free body diagram for the ladder. So I'm doing that right on the main picture here, but remember this is a free body diagram for the ladder. So that means the forces shown in the picture are forces acting on the ladder. Since the contact at point B is frictionless, the shear force at point B, which is the vertical force at point B, has to be 0, right? But there will be a normal force, and I'm calling that as B sub x. The contact at point A is frictional, and therefore we will have both the shear force and the normal force. So let's call those as A sub x and A sub y respectively. In a problem like this, we should always do a little planning first. In other words, we should figure out how we're going to solve this problem. First, we go ahead and list all the unknowns of the problem. So here we have three reactions, right? AX, AY, BX, and this angle theta. So there are four unknowns in total. Therefore, math tells us that we need four equations to solve for these unknowns, right? So this is a two-dimensional rigid body kind of problem, and therefore we can write down three equilibrium equations, right? We need one more equation that's going to come from the frictional law applied at contact A. So this is our plan. So let's go ahead and write down the four equations and solve. My first equation is the force equation in the vertical direction. I choose this to be my first equation because by looking at the problem, I see that this equation is going to allow me to calculate A sub y right away. A sub y is calculated to be 200 pounds. Now I'm going to take a moment about point B. So here's my equation. Why did I choose this to be my next equation? Well, I know this equation is going to bring AX and AY in it, right? But I also know that I can connect AX to AY through the friction law, right? We already found a value for AY, and therefore this equation is going to allow me to solve for theta. Here's my friction law. Friction law says AX, the shear force at contact A at the verge of sliding, should be equal to mu multiplied by the normal force at contact A, which is AY, right? Mu is given as 0.4, and therefore AX equals 0.4 multiplied by AY. After combining equations 2 and 3 and substituting 200 pounds for AY, this is what I have. So let's go ahead and simplify and find a value for theta from it. Solving for theta from this equation, I get a value of 51.4 degrees for it. Now I sum up the forces in the horizontal direction in order to find a value for Bx, and I get a value of 80 pounds for it. Here's a summary of the values we got for our unknowns. Let me also point out the following. So in the problem we just solved, the horizontal distance from A to C was given, right? Instead of that, if this distance is given, it turns out the math is slightly more complicated. So let's go through the steps to see why. The vertical force equilibrium equation is the same as before. Here's my moment equation about point B. Now this time, this term is different from what we had earlier. Earlier, we had a cosine theta term in here which kind of cancelled out with this term right there, right? So that led to a simple equation for sine theta, and we were able to find theta right away. But this time, they are not cancelling, and therefore, this is going to turn out to be slightly more complicated to solve. Like we did before, let's go ahead and combine equations 2 and 3 and simplify. When we do, this is what we end up with. To solve this equation, let's recall this trigonometric formula. Sin A minus B equals sin A cos B minus cos A sin B, right? The rest of the steps in solving theta from this equation proceed as follows. We're going to define a fictitious angle called alpha as this. We define a right triangle such that the adjacent side of alpha is 6.4 and the opposite side is 16. And then the hypotenuse, of course, works out to be 17.23. Now we take this equation and divide through by 17.23. Now we recognize that this is cosine alpha and this is sine alpha, right? Now applying this formula, the left-hand side of this equation can be written as sine theta minus alpha. Sin A cos B minus cos A sin B, right? Now we have a simple equation for theta minus alpha, and therefore theta minus alpha can be easily found from this equation. So I get a value of minus 16.87 degrees for that. And from this triangle we see alpha is tan inverse of 16 over 6.4, and we get a value of 68.2 degrees. So now we can go ahead and solve for theta by combining this with this. And I get a value of 51.3 degrees. If you compare this value with what we got earlier, you find that this is exactly the same as what we got earlier. This is not a coincidence. I kept it like this. In other words, I got this distance 5 feet to match the earlier problem. But if this had been something else like 3 feet or 4 feet, this value would have been different. But this is how you solve if this distance is given instead of this distance. This step of finding bx is the same as before, so I'll let you do it on your own.